Now, right now, we turned into the statistical analysis in Python. Okay. Firstly, we should give the main purpose of this topic. Statistical analysis in the research or the project management or your project outcomes are highly important because we should check our mathematical data or the numbers are statistically useful or not. We should check it. Okay. In the real world application, we can say that we can compare the sample means in clinical trials or scientific experiments. For example, in the biomedical application, we can take some measurements from the body or the human heart. Okay, and so these parameters like the pressure or the flow or the temperatures are highly contaminated with the noise. Okay, and so this measurements is meaningful or not should be considered in here, because if we take any data from the real world, we shall check its mathematical contamination or the mathematical brokenness should be controlled by the statistical analysis, because if this statistical analysis returns to the true values, and then we can say that this is meaningful and we can use it in real world applications. Okay, and so our objective is that we can test for significant differences between two independent sample, and we can use some methods in here. For example, conducting a two sample t-test using cgpi.stats. Okay, and so this t-test returns to this measurements is meaningful or not, is significant or not. Okay, and so we can easily set that the advantage of this controlling technique is providing a foundational approach for our hypothesis testing in research or in your design. Okay, this is important. This directly affect of this results is admissible or not. Okay, so we should create our example with these terms and import matplotlib.pyplot as plt, and from cgpi import stats. Okay, and we can generate the two sample but synthetic samples. For example, data 1 is mp random.normal 0 and 1 standard deviation 100 data, and data 2 can be assigned with the mp random normal and 0.5, 1 and 100. This some noise signal is contained in here with the values of the mean values of the 0.5. Okay, and we can use the t-statistic and p-values in here. You don't know anything about the t-statistic but p-value, but in the next session of your mechatronic lessons you will learn it. Okay, t-test in this can be calculated with comparing with these two data, and so we can fit this data 1 and data 2, and we can generate these values or these distributions are meaningful or not by using the t-statistic and the p-values. Okay, and so plt figure fig size is equals to 6 and 4. plt histogram data 1 alpha is equal to 0.75 7 and label data set 1. Okay, and 2 data set 2 and plt x label. This is the values of these terms because this is the histogram diagram, and so y label is equal to the what, the frequency, and plt title is equal to what, the histogram of 2 data sets. Okay, plt legend should be given in here and plt show must be called in here. Okay, and so if I run this code, and then we will have these terminations in here. Firstly, the dataset 1 is depicted with the what, the blue color, and the other one is the blue is depicted with the orange color. Okay, and so these statistical distributions may have same, but with what, with some mean error in here. Okay, and so how can we test this data? Firstly, we should print the t statistic value. It's given t statistic and p value, which is given the what, the p value. Okay, and so if I run this code, and then we will have the some 2 indices in here. Okay, and the p values is smaller right now, and t statistic value is returns to -3.6. Okay, but however, or what if I change this data to with the 0 and 1? How come this produces the effect of this code? Okay, and so right now the t statistic value, in the previous case we have the -3.6, but in this case 0.08. Okay, and but in the p value we have reached the higher dimensions, 0.93, which means that if the p value is higher, and then these 2 distributions or the measurements are what, are statistically meaningful. For example, you may have the 5 measurement from the pressure sensors. Okay, and this sensors contains the what, the 100 data, and so we have the 100 times 5 data or matrices in here for a given measurement. And then if we take, or if we apply the t-test in here, and we will get the p values at the highest one up to what, 90%, and then we can say that this measurements is okay for our applications. Okay, this is directly tells us to what, to these nominations. Okay, or if we rerun this code, and then at each case we have the highest p values in here, like this one. Okay, and we can say that if we take the what, the p values, it is the highest of the what, the 95%, and which means that this data representation or the measurements are okay, are current for our applications. Okay, this simple test was highly effective for our applications. Okay, so that's all for the statistical analysis. We should continue with the what, the numerical integration. In your mechatronic application, you have always utilized these terms in order to what, in order to create your applications. Okay, and so firstly we need to give the some brief about the what, the numerical integration, and what's the needing for this application, because we need to create what, or we need to take the numerical integration for our data. But what's the cause of these things? Real world applications or the real world examples can be given us to what, calculating the areas under the curves in signal processing or the physical path calculation. For example, if we have the some function which is equal to the what, the fx equal to the x, it's a linear function, and we can easily take the what the integration by using the analytical solutions. But in your real application, we have the some noises, or we will have some unknown data in here, and so we cannot formulate the analytical expression for this model. Okay, and so in this case we should use the numerical integration. Okay, and so calculating areas under curves in signal processing or any measurements in here. Okay, and so our objective is that computing the integral of a complex function or data representation. Okay, and we can use the adaptive quadrature methods in CGPy integrate. We can use another methods like the Ranch-Kata methods, or some simple Euler differentiation or the Euler integration method in here, but in CGPy integration we have the quadrature methods in order to be calculated the numerical integrations. Okay, and so what is the advantage of these terms? Advantage of this one solves the integrals or unknown model that are analytically challenging. Okay, but with high accuracy. Okay, so we need to build our example like this one, x1, the import numpy smp, import matplotlib.pyplot as plt, and from CGPy integrate import quad. Okay, and after that we can define the def integrand x function in here, return to the mp.x minus x over 2. For this function we do not have any analytical solution for for calculating this integral. We don't have any analytical solution to get the integral values of this function. Okay, I choose it, and after that we can take the integral and error values in here like this one, the quad integrand can be used in here 0 to mp infinity. This values is the starting point for for integrand. Okay, or integral methods. The otherwise is the upper limit up to infinity, and so this integral is calculated with with starting values of the 0 to to infinity values. Okay, and x values can be created in here, linspace 0, 5 and 100 data, and y values is equals to the integrand x values. Okay, and so this is our real representation of this function. Okay, and after that we can build the PLT figure in order to visualize the whole results in here like this on the fixed size 6 and 4 is given here. PLT fill between is a function of the x was, y was, in order to show the integral terms of these parameters, and color is sky blue. Okay, and alpha, the opacity rate is equals to 0.4. Okay, and PLT plot is the x was, y was. Okay, and label is equals to the x minus x over 2. Okay, and PLT x label can be assigned with the x label x and PLT y label is equals to the x over 2 but with the minus term, and PLT title can be assigned with the area under x minus x over 2, and PLT legend and PLT show. Okay, and so if I run this code and then we will have some figures in here, like this one. This blue skyline indicates what the area of the R generation. But what is the values of these terms, or the integral values of these terms? Okay, and so this plot is labeled in here, like this one, label X, this one, but we can assign to what the label values with the what integral values. Okay, and so if I run this code, and then we will have the area of these terms 0.88, okay, up to this code. Okay, but it's from the what 0 to infinity. Okay, what if I change this term with the 1? Okay, and so we decrease the values of the what, the area of these terms. And so just remember that this term cannot be solved by using the analytical methods, but with the numerical integration we can reach the whole data by using these terms. Okay, just remember that. This is how we can say, or we can build the what, the numerical integration on the what, on the system. Okay, this is some useful method for the what, for a given the any datas in here, like this one. So in the last topic we need to talk about the 3-5 osculatory system.py. Okay, so what's the purpose of this modeling osculatory system in engineering application? In the real world application, for example, we must simulate the suspension system in mechanical engineering or molecular vibration. Real world application is equals to the what, the suspension system design or the vibration models should be used or built in the what, in the numerical methods. Okay, and so our objective is that the solving a second order system, but ordinary differential equation ODE for a simple harmonic oscillator. Okay, and our method is transform to first order ODS and solve using the CGPy integrate ODE int. Okay, and so what's the advantage of this implementation? Offering the robust modeling and simulation for physical systems. Okay, so how can we do that? We should give the what, x1. Okay, and so in order to build your system, you may not know anything about the osculatory system, but you will learn it in the next sessions. For example, in the system dynamics or the vibration lesson or the any other mechatronic engineering lessons. Okay, but you need to utilize this function in order to solve these parameters. Okay, import ODE int. Okay, so firstly we should define the def harmonic osculatory system with the y and t. These are function x and v. This is the deflection and the deflection rate of the R system in here, and dy dt is equals to what, the v and minus 0,1 times v minus x. This is some simple second order differential equation form. You don't need to know that, but this representation gives us a time response of the suspension system or the any vibration system. It's given in here. Okay, after that we should define the y0 with the values of 1.0 is the deflection initial values, and 0,0 the velocity values of this deflection, it's equal to 0, and t is equal to mp lin space 0 to 10 101 data, and solution of this ODE int can be with what harmonic oscillator a0 initial condition and t time should be given here. Okay, and after that we should give the PLT figure fixed size, which is equal to the what, the 6 and 4 PLT plot t, and solution returns to the what, the whole row values. First column is the position of the R method, position matter. Okay, and after that the second term is returns to what, the velocity values. Okay, but in this case we should divide the set. Okay, and also line style should be different from the position values. PLT X label should be assigned with the time and Y label should be assigned with the values, the position and the velocity values, and PLT title simple harmonic oscillator, position and velocity. Okay, so PLT legend should be given in here and PLT show must be used in this case. Okay, and so we have the some problem in here like this one. Okay, yt x v y dy, and we should return the dy dt. I'm sorry. So if I run this code, and then we will have the simple harmonic oscillator in terms of what the position and the velocity values of these terms. Okay, and the blue line is the position, but another term is represent what, the velocity line. And so this is like the numerical integration, but in this case we should differentiate all the results by using this form. Okay, and so if we take this nomination and then this ODE can be run using the what, harmonic oscillator to generate the harmonic response, position and velocity values of the vibration or the suspension system in that case. Okay, and so this is the last example of the R session, and I hope you have learned about everything that I'm saying in this lesson. In the next lesson we will talk about the projects and solution using the Python programming language. Okay.